What happens when the satellites we rely on for everything suddenly disappear? Nobody wants to wake up in a world where the global supply chain is frozen in place, phone has no signal, and GPS won't load. This isn't a scene from a movie. It's a potential reality of the new space age, a time where Earth's orbit has transitioned from a vast, empty frontier into a fragile and crowded ecosystem known as an orbital house of cards. In this video, we explore the physics of orbital mechanics and how a single bad day in space could trigger the Kessler Syndrome, a runaway chain reaction that might lock humanity on Earth for generations. Every time you use a weather app, check a map, or even make a bank transaction, you are using a network of satellites orbiting hundreds of kilometers above. But this infrastructure is facing a crowding crisis. The low Earth orbit, or LEO, region stretching up to 2,000 kilometers is currently home to millions of pieces of debris, from defunct satellites to tiny paint flecks and rocket fragments. In space, size doesn't determine danger, velocity does. These objects move at approximately 28,000 kilometers per hour. At these speeds, a fragment the size of a marble carries the kinetic energy of a bowling ball dropped from a skyscraper. An impact with a 1-kilogram object is equivalent to several kilograms of TNT, capable of turning a multi-billion-dollar satellite into a cloud of thousands of new projectiles. This is the foundation of the Kessler Syndrome, a theoretical tipping point where the density of objects is so high that one collision triggers a self-sustaining cascade of more impacts. For decades, the Kessler Syndrome was seen as a slow-moving problem that would take centuries to develop. However, recent data published in 2025 has introduced a more immediate metric, the collision realization and significant harm crash clock. This metric measures how long we have until a catastrophic collision occurs if we suddenly lose the ability to maneuver our satellites. This isn't a doomsday clock, but a measure of orbital stability. In 2018, this window was estimated at 121 days. By mid-2025, due to increased orbital density, that margin narrowed significantly to 2.8 days. If our ground control or satellite navigation systems were knocked out for just 72 hours, a major debris-generating collision would be almost inevitable. This highlights why active space traffic management is no longer optional. It is a requirement for a functioning modern world. Why would we lose control of our satellites? The most likely trigger is our own star. Severe solar storms can heat Earth's upper atmosphere, causing it to expand. This creates atmospheric drag, pulling satellites out of their planned paths. During the geomagnetic events of 2024 and 2025, we saw thousands of satellites forced to use precious fuel just to maintain their positions. As we reach the peak of solar cycle 25, the synergy between solar activity and orbital crowding creates a complex puzzle for engineers trying to keep our eyes in the sky from drifting into danger zones. The primary driver of this new density is the era of mega-constellations. As of early 2026, there are over 14,000 active satellites in orbit, a massive jump from just 1,500 a decade ago. While companies like SpaceX have revolutionized global internet access, they have also created an unprecedented management task. SpaceX's Starlink alone operates nearly 10,000 spacecraft, accounting for over 60% of all active satellites. While these networks provide vital global internet, they have created unprecedented congestion. In certain busy regions of space, a close approach, where two objects pass within 1 kilometer of each other, happens every 22 seconds. Starlink satellites now perform an average of 4 collision-avoidance maneuvers every month. In the first half of 2025, these satellites had to dodge other objects over 145,000 times. We've reached a tipping point where the primary risk to a satellite is no longer old junk, but the sheer volume of active traffic. This has turned space into a global commons that requires constant automated supervision. We are already seeing signs that the orbital environment is reaching a breaking point. In August 2024, a Chinese Long March 6A rocket broke apart, creating a cloud of at least 700 to 900 trackable fragments in a highly populated region. In late 2025, the Tiangong space station sustained window damage from a tiny, untrackable piece of debris. Even our most advanced satellites aren't immune to failure. In December 2025, a Starlink satellite suffered a propulsion anomaly, venting its tanks and tumbling out of control while releasing hundreds of debris fragments. While these fragments deorbited quickly due to their low altitude, the incident showed that hardware failure can create an immediate tipping point in a crowded shell. A major debris cascade wouldn't just be a scientific tragedy, it would be an economic kill switch. The loss of GPS timing signals alone could desynchronize global financial markets and 5G networks, costing the economy billions daily. Before space becomes physically impassable, it could become economically Kessler, where the cost of insurance and risk outweighs the profit of being in orbit. Space is a global commons, and like the oceans or the atmosphere, it is vulnerable to overexploitation. Current international laws like the 1967 Outer Space Treaty are aging and lack clear mechanisms to enforce cleanup or liability. The good news? We are already seeing the transition from frontier to stewardship. New international guidelines now suggest a 5-year rule for deorbiting dead satellites, requiring satellites to deorbit within 5 years of their mission's end. Another solution is lowering orbits to 480 kilometers. SpaceX is also taking a proactive step in lowering 4,400 Starlink satellites. At this lower altitude, operators are ensuring that if a satellite fails, the atmosphere naturally cleans it up within months, not years. 2026 marks a turning point for active debris removal, with companies testing robotic capture bags and nets to deorbit the largest kinetic bombs. As we explored in our episode about Polish space program, Poland has become a fascinating example of this shift. A perfect example is PWSAT-3 from the Warsaw University of Technology. This student-built satellite is specifically designed to test a cutting-edge deorbiting system. By focusing on deorbiting tech, Poland is positioning itself not just for military surveillance, but as a key contributor to global orbital sustainability. We are at a critical juncture in our journey as a spacefaring species. The house of cards doesn't have to fall, but it does require international cooperation and smarter technology. Preserving our digital civilization depends on how we manage the next few years of orbital growth. If you found this deep dive into orbital criticality important, consider sharing it to raise awareness about the fragile state of our skies. Stay informed, and we'll see you in the next one.